Hello, and welcome to the second part to 6.6 exponential and logarithmic equations. In this second video, we're going to now talk about logarithmic equations and how to solve logarithmic equations using a one-to-one property, very similar to exponentials, and using the inverses to log, which are going to be exponentials. And we're going to start with the latter one, exponentials. How do we use exponentials to solve logarithmic equations? So here I have the steps on how to solve a log function using, again, its definition. What we need to do is that we want to express the equation in the form of log base b of some value m equals to a constant equal to a number, again, c. Using the definition of log, recall that log base b of m equals c means that our base is raised to this value of c and is going to equal to the input value of n. Doing that, we can then solve for the variable, and we just need also, because our domain is restricted, remember that our m value has to be a number that's greater than 0, a positive number. We have to make sure that the number that we find is going to guarantee that's going to fall within the domain of this thing. So what we're going to do is we're going to first check what the actual domain is, and then when we solve for the solution of x, make sure that that value falls within the boundary for the domain. So let's jump into the first example. So here's our equation, log base 4 of 2x plus 6. And we want to begin by first identifying what the domain is, like I mentioned. So what we're going to do to identify the domain is get this value here, our input value of 2x plus 6, and make sure that this value is always going to be a positive number. So whatever value that we solve for this equation, it has to be a number that's going to be positive every single time. So we have to set it to be greater than 0. So solving this equation, that's going to move the 6 to this side, making it negative 6. So 2x is greater than negative 6. And we're going to divide by positive 2. We're going to divide by positive 2. So the value of x will be greater than negative 3. So whatever solution we have, the solution has to be within the boundary of the domain. So that number has to be a number that's going to be bigger than negative 3. So we have the number 0 on our horizontal number line, negative infinity, positive infinity, and we have the number negative 3 here. Our solution has to be bigger than, not equal to negative 3, but bigger than negative 3 in order for this solution to count. So let's figure out what the solution is now. So to solve this equation, recall that the format of this thing is that if I have a log base b of some m value, and that's going to equal again to this exponent, I'll call it x, and I'll call this y, then that means that x is going to equal to the base raised to the second power. So all I need to do is get the 2x plus 6, that's my x, this value right here is the x, and set it equal to this base raised to this power. I wrote 2 because I was looking at the number there, but the base raised to the power of y. But this specifically, again, would be 4 to the second power. So as long as I have, again, my log isolated, that's the only thing that I have here, no horizontal dilations, no vertical dilations, no vertical shifts where I'm adding something out there, and it's log like this is the ideal thing to do. All I need to do is get what's in the parentheses, my input value, and raise that to the base to this power right there, using, again, essentially just the definition of what a log is. Now simplifying this, we're going to get 2x plus 6 equals 16. This requires us to move the 6 to this side, making it negative 6, and 2x equals 10, and then dividing both sides by 2, we find that the value of x is positive 5. Now, I kind of boxed in that answer prematurely because I need to verify that this number 5 falls within the boundary of the domain, and it does, because 5 is obviously going to be a positive number, and positive numbers by default are bigger than negative numbers. So positive 5 would be there, which falls again within the boundary of the domain. So this is how you find your solution and how you check that your solution still satisfies the domain. Now, if it didn't satisfy the domain, that would mean that x is not a solution, and this would just be an extraneous solution, and this equation has no solution at all. But since that didn't happen, we satisfy again the condition. We found that x equals to 5, which is a number bigger than -3. We don't have to worry about that. So here is your answer to example number 1. For example number 3a, I want to solve this equation here. Let's first recall what the domain of this thing is. So to find the domain of this, let me do this work right here on the side, our domain, and let me do it in blue. We're simply going to get our horizontal transformation of 2x plus 6 and make sure that it's set to be a positive number. So set it to be greater than 0. So solving this equation, that's going to move the 6 to this side, making it -6, and dividing by a positive 3. X has to be a number bigger than -2. So we're only allowed to pick numbers greater than -2. So to figure out what the solution, what specific value of x here for this log base 4, when multiplied with 2, added 6, gives us exactly this value of 2. Well, whatever the solution is, it needs to be a number that is greater than -2. If it's not, then this thing will have no solution, and there is no way of finding a number to make this thing equal to 2. So let's see how we do this. Well, in this particular example, we have it set up perfectly. We have our log isolated. We're not adding or subtract or multiplying anything in front. We're not adding or subtracting anything again to this entire thing. So we can go straight to the definition. So we begin by getting this exponent of 4, raising it to this power here, and setting it equal to what's in the parentheses. So in other words, 2x plus 6 equals 4 to the second power. So what you see, what I've just did, I simply get this value here, the value that we use to get the domain, and set it equal to the base of our log raised to this value there. And you're going to see again this procedure done on every single example. So pay attention to that. So now this is 2x plus 6, and 4 to the second power, that's equal to 16. Our value here is now going to get, well, we're going to subtract 6 from both sides, move the 6 to the other side, making it -6. So 2x equals to 10. Dividing this by 2, we get that the value of x equals to a total of 5. And now let's compare that to the domain. Well, again, our domain is x has to be a number greater than -2, and well, 5 is strictly a number greater than -2. So this right here is going to be our answer. So -2, all my answers have to be bigger than -2. And since positive 5 over here, yes, positive 5 falls within the domain. So this is our solution. Now, like I mentioned, just in case you didn't understand the first time, if I solved this equation and the solution here was a number that was less than -2, like let's say -5 instead, then this would not have a solution. -5 does not fall within the boundary of our domain. So this would have no solution if it happened to be -5. So similarly, let's look at this example. So here, the exact same thing. First, let's figure out what the domain is. So our domain will be determined by getting 15 plus 35 and finding the solution to this inequality. So we'll move the 35, to the other side. So 15x will be greater than -35. And dividing it by 15, x will be greater than, that's going to reduce by a common factor of 5. So -7 over 3. So we just need to get the solution to be bigger than that value, of -7 divided by 3. All I did was, again, divide both the 35 and the 15 by 5, the greatest common factor, and we end up with that. So now let's see what the solution to this is. So again, in very simple terms, what we're essentially doing is just simply getting this 15x plus 35 and setting it equal to this base of 5 raised to that power of 3. So 5 to the third power. Well, 5 to the third power, that is, let's see, what is that equal to? 5 times 5 is 25, so 125. And now we can solve the equation by, and from here we solve this equation by subtracting 35 from both sides, which is 90, and dividing 90 by 15 is 4. No, not 4, 8. Scratch that. 6 there. 6. 90 divided by 15 is 6. Now moving on to the next example. On this example, we can start straight into getting this equaling it to our base to the 14th power. Because we're multiplying again a 3 and a 2 on the outside, we have to get rid of this outer again operations, these vertical transformations, so we can isolate again the natural log of x. So we want again basically letters to the left, numbers to the right. In this case, the natural log of x to be the only thing on the left side. So the best way to start here is to move the 2 to the other side. So we're going to subtract that 2 from both sides. And then we have 3 times the natural log of x equals 12. Dividing now by 3, we get that the natural log of x equals 4. And in this example here, our solution is going to be this value. Yet again, we get this value inside the parentheses x, and we set it equal to the base of our natural log raised to this power. So your job here is to remember that the natural log is a log of base e. So let me move this down, and let me rewrite ln as a log base e of x. So that means that x equals e to the 4th power. And again, you're not going to write decimals, so no decimals allowed here. Write your answer again in this format in the actual solution, so e to the 4th power is the actual answer here. Similarly, in this example, here we have the common log, so we want this to be isolated. So we want this to be by itself. So we have to get rid of this, and then we have to get rid of that. So starting off with the minus 7, probably the best way of starting is to get rid of the minus 7 by adding 7 to both sides. You can get rid of the 4 by dividing everything by 7, but it makes the numbers a little not as easy to work with. Not impossible, just not as easy. So this adds up to 16. And now if I wait to get rid of the 4 by dividing by 4 at the very end, 16 divided by 4 is a lot easier to work with. So this is a total of 4. Now, again, from here, it is your responsibility to remember that the base to the common log is a log base 10. So this is log base 10 of x equals to 4. So you have to be familiar what those special notations are for our logs, our common log and our natural log. So here the value of x equals simply to 10 to the 4th power, which is 10,000. So that right there would be your value. Now, if you had more operations inside here, of course, you would have to solve the value for x. So let's say instead of 4 times the log of x, we had x minus, you know what, we'll do 2x minus 100 minus 7 equals 9. Okay, so the same first two steps we'll do. These two things will be done, and eventually we'll end up with log of 2x minus 10 equals to 4. So 2x minus 10 equals, again, like I mentioned before, 1,000. Because we're going to do everything the exact same way. The only thing that's going to change here is that we're not going to stop at 1,000 because of this part right there. So this just simply requires us, again, to solve the equation by adding the 10 to both sides and then dividing that answer by 2. So 2x will equal to, 100. That was supposed to be 100 originally. 10,100, because I'm adding that to both sides and then dividing it by 2. X is equal to 5,500. So that right there would be your solution. So you see, it goes through the same procedure. The only difference is that you have to do a couple more steps in order to solve the equation for x. After you rewrite this, and after you rewrite this in this format right there to get this value, you just have to, again, make sure that you solve the equation for x. Now here I would check that the domain, again, is a number that's going to be bigger than that value there. I didn't do that over here, and I probably should have done it right here since we've isolated the x. X would have to be greater than 0, and this number is going to be a number bigger than 0. 2.71 to the 4th power is a number bigger than 0, so I don't have to worry about that value there. And the same thing with this value right here. From here, I need this to be a number greater than 0, and 10,000 is bigger than 0. Here, I would need this value to be bigger than or equal to 50, because getting the domain of that would be 2x minus 10 greater than 0, means that x would have to be greater than 50. And obviously, this number is a number bigger than 50. So we're good on that. So now let's say that we're adding two logs together. As long as the bases are the same, again, we can use our product property, and to add these two logs of these two different values, I multiply them together. Now, before I go into solving the equation, well, let's talk about, again, the domain. Can't forget that since I kind of overlooked that in the last two examples. So for here, we have two logs. The first log is just log of x, so x needs to be bigger than 0. But for the second one, let me highlight it in purple. For this one right here, to get the domain of that, I need that x plus 7 to be greater than 0, which means that x would have to be greater than negative 7. So here, the domain needs to satisfy both of these conditions. That x has to be a number bigger than 0, and that same x has to be a number bigger than negative 7. So if I look at this as a number line, just so I visualize, I have 0 here, and I have negative 7 there. So I need the numbers to be bigger than 0, not including 0, and I need the numbers to be bigger than 7, not including 7. Okay, so I need to make sure that it satisfies both conditions, not one or the other, but both. So in order to satisfy both conditions, it has to be over here, it has to be a number bigger than 0. Because if I pick a number smaller than 0 and only put right here, that's not going to satisfy this condition there. So I have to make sure that I satisfy that condition right there. This right here will guarantee me that it's a number bigger than 0 and obviously a number bigger than negative 7. So let's see how we figure this out. So like I mentioned earlier, in order to solve this equation, I need again to have the format of a log by itself. So I can have two logs. So what I need to do is condense it to one single log of base 2. And what I'm going to do to these values here in yellow is that I'm going to multiply, and since I'm adding them, I multiply those two things. So x times x plus 7 is going to be x squared plus 7x. And now that I have my format that I want, I have my log by itself, and it equals to a constant, I can get this value here and set it equal to this base of 2 raised to this power of 3. So x squared plus 7x equals a total of 248. Now, this cannot be done using, again, the same technique as linear equations because it's a quadratic. So instead of doing letters to the left and numbers to the right, I'm going to do everything to the left power. As soon as I see an x that has a degree or an exponent of 2 or higher, I need to move everything to the left side and use some type of factoring technique in order to solve this equation. So right here, because it's a quadratic, I can use the standard factoring technique of breaking my x squared into two identical factors of x and x, determining the sign. So this would be positive, and a positive times negative is negative, so different signs. And then looking for the factors of 8 that will add up to 7. So 1 times 8, 4 times 2 are the only options. And since one is positive and one's negative, it would have to be a positive 8 and a negative 1. So those two numbers multiply to give you again this negative 8. But then a positive 8 plus a negative 1 adds up to the positive 7 that we need to match up in the middle. So solving now here, the way that we get the first factor to equal to 0 is that x would have to be equal to negative 8. And the way to get the second factor equal to 0 is x would have to be positive 1. Now, going back to the domain here, remember again, like I stated earlier, we have to make sure that our x value is not only bigger than negative 7, but more also bigger than than 0. So that eliminates negative 8. Negative 8 is not bigger than negative 7, and it's not bigger again than 0. Again, it has to satisfy both conditions. So this number is an extraneous solution. So in very simple terms, what that means is that it doesn't count as a solution. The only solution that this thing actually has is this solution right here. X is going to be a 1 is bigger than 0, and obviously if it's bigger than 0, it's bigger than negative 7. So this is the only solution that this equation has. Even though we mathematically and algebraically found two solutions, this one doesn't count. It's again referred to as an extraneous solution. So for this example, let's look at the same thing. We'll start with the domain. And for this value, x would simply have to be greater than 0. And for this value right here, x minus 6 would have to be greater than 0, which means that x would have to be greater than positive 6. So let's visualize this on a number line. We have 0 and we have 6. So our values have to be greater than 0, but again, cannot equal to 0. And they have to be, 6, and they have to be greater than 6. So they can't equal to 6. So when we solve this equation, the values of x that's going to satisfy both of these is going to be anything that is bigger than 6. As long as my answer is bigger than 6, it's going to satisfy both conditions, it being a positive number, a number bigger than 0, and a number bigger than 6. So you see, anything that falls within here is not going to satisfy this second condition. So we need to make sure that it's just simply bigger than 6. So if you notice, it's always just again the number to the right. So we look at the two numbers, look at the number on the right, and we just have to again see the values greater than, well, because it's greater than. Oh, why does it keep erasing? It has to be greater than, so it has to be greater than. Same thing right here, greater than 6. So that guarantees that satisfy both of these bullets there. So now let's go into how to solve this. Well, just like the last example, since we're adding again these two logs, we can condense this to 1 log of base 4 by multiplying the x with the x minus 6. So that gives us x squared minus 6x equals 2. That means that this will equal to this base of 4 raised to the second power, which is a total of 16. And because this is a quadratic, x to the second power, that means to solve this, we're going to move everything to the left side of the equation and set it equal to 0. So on the left side, the positive 16 becomes negative 16. And because it's a quadratic, we can try our basic factoring technique. So we start by splitting the x squared into 2 equal factors. Since this sign is negative, we're going to make that a negative symbol, and a negative times a negative is positive, so we'll make this into a positive sign. Now, let's look at the factors of 16. What factors of 16 can give us 6? And remember, the signs are different, so I need to subtract them, because when I add a negative and a positive, the rules for that is to subtract the two values. So 1 and 16 won't work. 2 times 8 looks like that would work. 4 times 4 won't work, because a negative 4 and a positive 4 is going to give us 0. So a negative 4 plus a positive 4 equals to 0. And we want it to match to this value right there, not to the 0. We need to match to that number there. So 2 and 8. So if I make the 8 negative and the 2 positive, voila, that works perfectly. A negative 8 plus a positive 2 equals negative 6. So there are my pair of factors of 16 that I'm going to use. So this means that x would have to equal to positive 8 and x would have to equal negative 2. Now, even though we found two solutions here, both of these solutions are not going to work, because our domain states that we have to be a number bigger than 0, positive. They won't satisfy this right there. If I plug in negative 2, the log base 4 of negative 2 doesn't exist. So that doesn't satisfy this part right there. Nor does it satisfy that part right here either, okay? X has to be bigger than 6 as well. Well, negative 2 is neither bigger than 6 nor 0. 8, however, is. Let me scratch this out. 8, however, is. 8 does satisfy both conditions. 8 is a number that is bigger than 0, and 8 is a number that's bigger than 6, so it satisfies both of them. So this is not an extraneous solution, and this actually works and fits in the equation. So again, recall, just to back up again and to recap here. When you solve this equation, just because you end up with two answers, or even just because you end up with a positive answer or a negative answer, doesn't mean that they're both going to work, okay? And just because this is negative doesn't automatically make excluded. Okay, we have to make sure that it satisfies both conditions here, and it just so happens that it doesn't satisfy, again, the first part, well, neither part. So we can have answers that are negative, but here it just can't work because we're not doing any type of operation. So we need something to be positive every single time. And we also need that positive number to be a number bigger than 6, which 8 satisfies the case. Now for the last two examples, we're going to use the one-to-one property that logs have. This is very similar to exponentials. That if we can express one log on the left equaling to the exact same log, in other words, that the bases are the same, then I can use again the fact that m and n are going to be equal to each other. The values of the logs are going to be the same. This involves again using a single log with coefficients on 1 on each side of the equation. I can then solve the variable, and like always, check that my solution is going to be a value that will guarantee me that this value here is a number bigger than 0. So let's figure out again the domain. So that just means I need to check what my domain is. So let's start off with this one right here. So for the domain for that one, I need x plus 3 to be bigger than 0, which means that x would have to be bigger than negative 3. And this one right here means that x minus 2 would have to be bigger than 0. So x would have to be bigger than positive 2. So let's visualize this. Right there. Well, I need to again condense this. The only way that this one-to-one property works is that I have one log on the left and one log on the right. So in order to simplify this side over here on the left side, I'm going to add those two things by multiplying the x plus 3 and the x minus 2. So I'm going to multiply x plus 3 and x minus 2, which is going to be x squared minus 2x. I'm just going to distribute plus 3x minus 6. So again, what I'm doing here is multiplying x plus 3 and x minus 2. So I can condense this into one log. And that's going to equal to the natural log of 14. So as you see here, this and this are the same, so I can now ignore them. And that would mean that x squared minus, this is 1x, positive 1x minus 6 equals 14. Now, again, because this is a quadratic equation similar to the last two problems that we did, we need to move everything to the left side and change that positive 14 to a negative 14. Set this equal to 0. And if I combine these two terms, which I can, that gives me a total of negative 20. And voila, look at that. I have a quadratic which hopefully can be solved by using our standard factoring technique. So x and x, positive and negative, and the factors of 20 that can add up to a positive one with a positive and negative factor is 5 and 4. So if I make this 5 and I make this 4, positive 5 plus a negative 4 equals to that positive 1 we want to match up and get in the middle. So this means that x equals negative 5. And for the second factor, the value of x would have to be positive 4 in order to get this equal to 0. So now let's go back to our domain. Remember, from our domain, we concluded that the values of x have to be bigger than 2. So negative 5 is not bigger than 2. So this one is out. And the only solution that we have is x equals positive 4. Now, in this example, similarly, before we actually get into solving, let's identify what the possible domains are. So when we get the solution, we make sure that we can eliminate any extraneous solutions. For the first one right here, x plus 2 would have to be bigger than 0, which means that x would have to be bigger than negative 2. For this one, 4x plus 3 needs to be bigger than 0. So 4x is bigger than negative 3, so we move the 3 to the other side. And now dividing by 4, x is bigger than negative 3 divided by 4. And for the last one, 1 over x would have to be bigger than 0. So if I get the reciprocal of this, that means that x would have to be less than 0. Let me take that back. That should still be greater than 0, because all I'm doing to get the reciprocal, because it's 0, x would have to be greater than 0. All I did was just flip this, okay? So if I flip that, that's going to just keep, again, 0 is going to flip, well, it should flip 0, but it's going to keep it as 0. So our domain is going to just be values like that. So let's see, now let's solve for this, okay? So in order for this to work, remember, we need one log on the left side. Here we have 2 logs on the left side and 1 log on the right. So in order to condense this on the left to one single log, these values have to be divided. This value of x plus 2 needs to be divided by the value of 4x plus 1. But we're not going to use any type of long division. We're simply going to write it as the ratio of those two quantities. So here the log of x plus 2 divided by 4x plus 3, and that's going to equal to the log of 1 over x. Now going back, oh sorry, let me back up a little bit. So for the domain, let's visualize what this looks like. We have the number negative 2, we have the number 3 over 4, which is 0.75, negative 2, negative 3 over 4, and we have 0 over here on the far right. Since all of our values have to be bigger than these things, the way to make sure that we again satisfy all of them, just simply focus on this part right here, the one on the very far right. So as long as I make my values of x bigger than 0, that's going to satisfy the condition that x is going to be bigger than that, and that the x is going to have to be bigger than that. So as long as x is bigger than 0, that satisfies all three conditions, because 0 is to the farthest to the right. And since everything is going to the right, I look at that value there. Now, going back to our equation, how do we solve this? Well, first, we drop the logs. Since we have logs again, the same log on both sides, x plus 2 divided by 4x plus 3 equals to 1 over x. And to solve this simply requires us to use cross multiplication. So I'm going to start by multiplying these two things together, which was x squared plus 2x, distributing the x, and then multiplying these two things together, which is 4x plus 3. Now, since one of the x's is an x to a power other than 1, greater than 1, that means we're not doing letters to the left, numbers to the right. As soon as you see an x with an exponent of 2 or higher, we're going to bring everything to the same side, to the left side. So that will be x to the second power plus 2x minus 4x minus 3 equals to 0. We have a set of like terms here, the 2x and the 4x. So that adds up to negative 2x minus 3 is equal to 0. And let me just highlight again how I got this number here by combining these two terms. And look at that. We have a quadratic that hopefully can be solved by factorization. And I'm starting to see that we can. Negative times negative is positive. And since 3 is a prime number, the only factors of 3 are 1 and 3, which work. Because if I make this a negative 3 and make this a positive 1, those two numbers are going to add up. Those two numbers add up to a negative 2. So that means that the solution to this is that x would have to equal to a positive 3 in order to make the first factor equal to 0, and x will equal negative 1 in order to make the second factor equal to 0. Now going back to our domain here, our extraneous solution is negative 1. X can only be values bigger than 0, and 3 satisfies that condition. 3 is going to be over here on the number line, which obviously is to the right of everything right here. Negative 1 would be found here, and that doesn't satisfy everything, okay? Our answers need to be to the right of all of these values, and 3 satisfies that. So this is an extraneous solution, and this is the solution to this equation. X would have to equal to positive 3 in order to get this to equal to that. So now this concludes the second part to 6.6. I hope you found these examples helpful, but if you do have any questions, please email me, send me a message from Marron Square, or check out the individual videos that are attached to the homework problems to guide you through how to solve that individual problem. Now, if there are any errors, any technical issues that you might have watching videos, or the link isn't working, please also bring that to my attention so I can update it and go fix any errors again, fix any technical support errors that you need. Thank you again for watching, and I hope you have a great day. Goodbye.